Let's say you want to do an ANOVA because you have more than two things. You can't do a t-test. So we have 4 treatments here, a control with 3 different things. So you want to see what's going on there, if there's any significant differences. But let's say you are working with a sensory panel, and you're wanting to keep your panelists calibrated to some extent. You want to see if there's any significant difference within the panelists, right? Because, you and I might perceive things as different on the sweetness scale. So that's the answer to your question. Or that's an example that may answer your question, is if we have multiple factors. In the thickener case, we only had one factor that we cared about. It was the thickener, whether there was a thickener and which thickener it was. That's one factor. We had 4 or 5 treatments there. 1, 2, 3, 4, 5. But if you were working over here, we have 2 factors. One factor, which has to do with the sweetener level, and another factor, which has to do with the panelists. One has 4 treatments. Another one has 5. So that's where we're going with this, is wanting to look at and compare all those differences at the same time. So if we look at the factorial design, you could have factor A and factor B. So we're going to go from low to high. That's what the minus and the plus refer to, low to high. In this case, with the one I just showed you, it would be a 4x5 design instead of a 2x2. Okay, and then what we'll work toward is finding some sort of, figure out if there's an interaction effect, and I'll explain that here in a little bit. So we have main effects, which if we go back here, the main effect might be just sweetener level or panelist. And then we could have an interaction effect where it might be like, is there something weird that happens when like a particular panelist tastes more sweetness? Do their tongues just taste a lot more sweetness? And some examples of this might be vitamin D, if you're looking into nutrition, and calcium in nutrition absorption. Like if you want to absorb nutrients like proteins or fats, if you have enough vitamin D, that helps. If you have enough calcium in your system, that helps as well. But if you have both, the proper amounts of vitamin D and calcium, there's like a synergistic effect. It's like you go from absorbing 10 grams of whatever that nutrient is to like 100, because it's just, the whole concept of 1 + 1 is 3. You're wondering, is 1 + 1 = 2? Or with this AB part of the matrix, does 1 + 1 = 3? So if we visualize that here, if we look at the first one where there's no interaction effect, we have factor B, where it's either low or high. Those were the treatments. We only had an A of 2 treatments. And if we have factor A, where the blue one is the low treatment, so this, let's say this is calcium as factor B, and factor B is vitamin D. So it's, in this case, if you consume higher amounts of calcium, you get more nutrient absorption. And here, if you consume more amounts of vitamin D, you get more nutrient absorption. So it's a simple, you do more, you consume more of this, you get a better result. So there's no interaction effect, if that makes sense. This will take a little while for you to kind of wrap your mind around it. But just compare this graph to this one. Let's say if you consume, different scenario, I should have came up with a better example, but let's just go along with that example. Let's say for some reason the system's different, and if you consume more calcium, which is factor B, if you have low amounts of vitamin D, you get better nutrition absorption. But if you have high amounts of vitamin D, you get lower. You see where we're going with that? The null hypotheses basically look the same. I'll have an example here in a little bit, but here we're saying this is basically one of the one-way ANOVAs, and this is another of the one-way ANOVAs. But where we're going with this is looking at the same type of ANOVA table, except we have a B in addition to the A, and we have the interaction. And we're going to look up these test statistics and see which one's significant. So you could have a situation where there is a significant difference within glucose in this example, and there might not be one within oxygen, and who knows, we'll see if there's an interaction effect. Just pretend that one of these lines is not there. And we're just looking at that blue line. That's all that you can do in a one-way ANOVA test, right? You can only compare things within one factor. In the case study, we were looking at the different levels of sweetener or thickener. That was one factor, is whether there was 10% sweetener in there, 20% or 30%. And actually, to be a purist, I should draw another point. I'll do it in blue if it'll let me. That's blue. Let's say we have 3 points. 1, 2, 3. That's what a one-way ANOVA is all about. We would do a t-test, but we can't because there's more than 2 levels. Or maybe it'd be more clear if I said, I'll try blue here. What if we had another point right here? Levels 1, 2, and 3, where this is low, medium, and high. That's what a one-way ANOVA is. You guys know what that means, right? And so it's very nice if you only have one factor, like how much sweetener or which thickener is in there. And two-way is handy when you have 2 factors. So if you try to wrap your mind around this, we have 2 factors. What are they? Factor B is on the x-axis, and factor A is on the y-axis. And then within each of those, we have 2 treatments, also called 2 levels, low and high. So these two-way ANOVAs are a very nice way of comparing everything within one chart. Because the alternative would be to make one chart for the factor A and another chart for factor B. See how we're just overlaying them on the same chart? Okay? So if we just focus on the chart on the right, how would you interpret this chart? Let's just take it one at a time. So if you add higher levels of factor B, do you get increased results? Yes, right? If you go from low to high, you go from like 2 to 6 on the low factor A treatment, and from 5 to 9. So it's about a 4-point difference. Doesn't matter which factor A we're thinking about. If you add more factor B, you get an increased result. Okay? So what about factor A? If you have higher levels of factor A, do you get increased results as well? No matter how much factor A you have, no matter how much factor B you add, if you add more, you get more. Pretty simple, right? So, I mean, you could do 2 separate one-way ANOVAs, and it would show that the more you give of a certain treatment, the more you get in terms of the y-axis. So pretty simple, not too groundbreaking. Okay, so I think we understand the graph on the left. So let's transition to the one on the right here. Okay. What happens if we add more of factor B? If it increases as long as, if we go from blue to red, it increases if we're talking about high levels of factor B. But it decreases if the parameters include the low amount of factor B. So it depends. It's an interaction effect. And that's the kind of thing that if you just ran two separate one-way ANOVAs, like if that was your result, and you had factor, let's say this is factor A, and you did another one with factor B, I mean, you might get some sort of bar graph, but you wouldn't be able to see the interaction effect. You just wouldn't, until you put them both on the same chart. You don't get to do that. Okay, so that's the value of two-way ANOVA. Is you can see, does some sort of synergistic reaction happen when we have both things happening at the same time? And this morning I was having a little bit of deja vu, thinking, oh yeah, that reminds me of my master's thesis. We were interested in enzyme kinetics, and we were trying to shut down the chemical reaction that spoils milk. It's not all microbiological. There's an enzyme in there called plasmin, and the precursor to that is plasminogen. And we were interested in how to shut it down. And so we had these different, see how we have 1, 2, 3, 4, 5, 6 levels of heat. The control, I think, was like 37 degrees or something like that. It's been a few years. And we have another factor, which is whether it has the plasminogen in it or not. It doesn't really matter exactly what that is. But notice how if you go up to 75 degrees or 65, you know, there's no interaction effect. But as soon as you get above that, you get some sort of interaction effect. It's just weird because you don't get this side-by-side pattern. So anyway, where were we? So remember how with one-way ANOVA, we calculated the sum of squares for the treatment, and we calculated the sum of squares for the air, where the treatment sum of squares plus the air sum of squares equaled the total. And we did that whole calculation to solve for the mean square, I guess it was the mean square air. We needed this one so we could solve, or I guess it was this one. Anyways, so it looks very familiar to the one-way ANOVA, in which case we were only interested in one factor, which in this case would be treatment, or the factor A, and there's different levels there. And so in that case, you would say, you know, let's say treatment, if this is A1, is the same as treatment A level 2 is the same as treatment for this is, we're still talking about A, the third level of A. That's what a one-way ANOVA is. But in a two-way ANOVA, we're introducing another factor, which would be B. We're also interested in this interaction effect. The idea is that we have three hypotheses. I just drew out the one for the factor A, which is that all levels of factor A are the same as each other, and if you got a F test statistic that was larger than the critical value that you looked at the table, then you would say, I'm going to reject that null hypothesis. One of these is different, and then you could do the means comparisons and jump using a Tukey, or the one where it shows you the different letters based on which one's different. Well, in this case, we're going to do the same. We're going to have another hypothesis for level or factor B, where we're going to say treatment B1 is the same as treatment B2, which is the same as treatment, let's say there were 3 total again. You would just say the null hypothesis is that all 3 levels of factor B are the same. And then we're going to have another set of hypotheses, or for the interaction effect, where we say there is no interaction effect, or there is one. Those are going to be the null and the alternative hypotheses. So that's how this works. So to backtrack a little bit, that's what this is showing, is you are working with 3 separate sets of hypotheses. Okay. And although I'm not going to bother to take the time, it would take another week or 2 that we don't really have this semester. We wouldn't get to go into acceptance sampling, so we don't have time to bother with the math, but just take a minute to appreciate all of the calculations that you would have to do. Think about figuring out sums of squares for treatment A, or factor A, factor B, and then the interaction effect. Holy cow, it is very meticulous. And you would need to figure out, well, how many degrees of freedom are there within factor A, factor B, and the interaction effect, because I'm going to divide the sum of squares by that to get the mean squares. And then I'm going to divide this mean square by this one, and then I'm going to, it's a lot. So thank goodness for computers. Okay. But you get the idea. Eventually, we'll compare this to an F critical value that comes out of the table of, F critical values depending on your alpha level. Remember, we're just kind of calculating where did my F test statistic end up? Is it right here? And then we're just going to look up out of the table where the critical value, remember, if it's over here, we're going to reject the null hypothesis. If it's over here, then we're not as extreme as the critical value, so we're going to accept the null hypothesis. Everyone with me? That should be a little bit of review, but a little repetition never hurt anybody.